Welcome. Today in this lecture, we shall be continuing the mathematical solutions of some other kinds of macroscopic balance equations, and in this lecture, we shall be looking into the inexact first order ordinary differential equations and homogeneous and heterogeneous equations. So, first let us take up this inexact differential, and in this case we shall be using some integration factor. So, you see that what we learnt in my earlier lecture was that the exact differential is one in which we found that when we are rearranging the equations in the terms of the mxy into dx plus nxy into dy equal to 0. So, we wrote this equation, and there we said that when in this particular equation we have dou m by dou y equal to dou n by dou x, then we have the exact differential, and we said that these kind of situations happen when in the particular parameter is not a path function but a state function. Okay? But in many cases, like in case of work, in case of heat transfer, etc., we find that the particular variable is not a state function but is a path function. So, in that case we shall be having this kind of situation where we shall find that dou m by dou y is not equal to dou n by dou x. So, in that case how do we go to solve this kind of problems? So, in this case we put some kind of an integration factor, so that to convert the inexact differential into an exact differential form. And here we assume that the integration factor, here it is small correction, it will be integration factor. Okay. So, in this case we find that this integration factor is a function of both the independent parameters, that is x and y in this case. Now, with this knowledge, what we do is this, that if I is the integration factor, we multiply this equation, this parent equation with I. Okay, this particular equation we multiply with I. And now you can see that this particular equation can become exact, that is, let us put in this fashion, like we put that dou m by dou y equal to dou n I n by dou x, this is the particular condition for exactness. Okay. So, with this is a condition for exactness. Okay. So, if this equation becomes exact if we have this particular situation. Okay. Now, what we do, we simply make this expansion for dou I m by dou y, that is I dou m by dou y plus m dou I by dou y, and similarly we do this break it up this particular differential as I dou n by dou x and plus n dou I by dou x. Okay. Now, after this particular transition, what we do is this, that let us first assume that I is a function of only x. In general, I is a function of only both x and y, but first we are assuming that I is a function of only x. Now, if that is the case, then we find that dou I by dou y will be 0. Now, in that case, from the previous equation what we have just find out this equation, we can put this dou I by dou y equal to 0, and then we obtain this particular equation. And after this what we do, we just rearrange the equation like this, that we simply divide this whole equation by mi. So, sorry, ni. Once we divide this equation by ni, we get this particular equation. And now what we do, we keep this particular term on one side and take this term on the other side. And what we are achieving by doing this kind of arrangement, what we are finding that 1 by I dou I by dou x becomes purely a function of x, and that we are calling is r, and this r is nothing but this 1 by n dou m by dou y minus dou n by dou x. Now, because this is a function of only x, that means this whole term should also be a function of only x. Okay. Now, what we do, r will depend on x only, and it may be variable or constant, and so we have, once we integrate this particular equation, we find that we shall get logarithm of I is equal to r, okay, and then we basically we put this an exponential term r dx we do. So, it becomes that I equal to exponential of this integration of rx into dx. Okay. So, once we do this particular manipulation, we would be able to get the value of the integration factor, provided it is a function of only x. Now, we have to also see that in all situations it may not be function of x, it may be function of only y. So, let us take that situation. It is similar to what we have done just earlier. So, here if we have I as a function of only y, then dou I by dou x will be 0. Again, going back to this particular equation, what we do, we take this particular term as 0. Then we find that we have this equation. Okay. Again, we divide this whole equation by mi, and then we get this particular equation, and we retain this term on this left hand side and take this term on the right hand side. And what we gain by this, we find that this particular term is a function of only y, and let us call this term as r star, okay, to distinguish it from r, that is the 1 by I dou I by dou x. Okay. So, this r star is nothing but this particular term. That means, this particular term should also be a function of only y. So, again we do the integration as before. So, it will be logarithmic of I equal to r dy. So, I equal to exponential r star y into dy. So, this is the way we are getting this expression for I if I is a function of only y. Now, let us implement this particular concept for this given example. Here we have been given this particular equation, as you can see here. Okay. Now, we shall see that this is first we have to check whether this is exact or inexact. So, for that we understand that this particular term is mxy in general, and this particular term is n x y. Okay. So, after identifying this m and n, then what we do, we find the this differential, that is dou m by dou y, and we find this is coming out like this, and then we see dou n by dou x, that is coming like this. Now, what we see from these two expressions, that dou m by dou y is not equal to dou n by dou x. That means, we have inexact differential. Now, once this is the case, let us try to see whether we can find some integration factor which can make this particular system exact. Okay. So, following our earlier derivation, now what we see, that r is equal to 1 by n dou m by dou y minus dou n by dou x. So, we put the value of the n here, and we find the value of dou m by dou y and dou n by dou x, and we get this particular terms. Now, we see that r is function of both x and y. That means what? That if I is a function of only x, then we should have r as function of only x. Now, because we find that r is a function of x and y, it means I is also a function of x and y. From this we are finding this. Okay. So, we should not be using this particular way of finding the integration factor. Now, let us look into the other way. If we assume that I is a function of only y, that is, let us check. Okay. Now, for that what we do, we find the r star, that is as 1 by m dou n by dou x minus dou m by dou y, and we find this is coming to minus 1. Okay. So, this shows that r star is a function of only y, may be considered to be that. How? This minus 1 may be written as, minus y to the power 0. Okay. So, we can say that r star may be considered to be a function of only y. So, if we can write it like this, then we find that here the r star is a constant. So, if we integrate it, so we find that I equal to exponential of this integration r star, that is minus 1 into dy, and that is coming I to be e to the power minus y. After getting this integration factor, what we do? We go to our parent equation and multiply both the sides with that e to the minus y. So, we are getting this particular expression. So, you can easily see that this was our parent equation. If you multiply this whole equation by e to the power minus y, you have to simply multiply this equation, that is our integration factor. Okay, this is I. So, if you multiply this whole equation you are multiplying with. Okay. So, you find that what you are having, that from here you are taking out that e to the y, it is e to the x only plus y dx into here x minus e to the power minus y. Okay. So, that is what we are obtaining here. So, this is how we are getting the exact differential, and now I am not going into the solution methodology because this I have covered in my earlier lecture. So, find that this is the particular generalized solution we get, and here we have this c as the some constant of integration, and this may be obtained from this particular thing, this particular initial condition we are given. So, what you can do, that you can see that we were given that at y equal to 0 we have at x equal to 0 we have y equal to 1. So, what we can do, if you put here x equal to 0, that means e to the power 0 plus 0 into y is equal to e to the power plus e to the power minus y, and this is also equal to this y is given as minus 1. So, you put this as minus 1 . So, you can put it as minus 1 over here and plus e to the power minus of minus 1 equal to c. That means, this is going to give you 1, this is 0. So, 1 plus e equal to c, that means c equal to this value. Okay. So, simply you can replace this c with 1 plus e. Okay. So, that is how you are able to get the value of c for this particular equation from the initial condition. Now, let us come to the next type of these ordinary differential equations, linear ODEs. In this what we are seeing, again the structure may be a homogeneous structure or a heterogeneous structure. Okay. Now, let us consider this particular system of the ODE. Here we have y prime equal to p x into y plus r x. Okay. So, now if we have r x to be 0, then we find that we are having y prime plus p x into y is equal to 0. Now, this particular thing is called homogeneous form. Okay. And this thing, you many times you get this kind of term, maybe then when there are no source terms in the balance equations, you may land up with this kind of homogeneous ODE. Okay. So, in that case you can see that it is much easy to get the solution, as you can separate the variables very easily. So, you can see that if you write you can write this equation as dy by dx plus px into y equal to 0. From here you get that dy by y is equal to minus px into dx, and then you integrate. Okay. When you integrate, this will give you the this. Okay. That means, y will be equal to exponential to the power this whole thing. That means, this y will be equal to this exponential to the power minus px dx plus some constant of integration. So, that is how you are getting this particular expression. Okay. Now, you see that this particular value of this integration constant may be again obtained from the initial conditions of the given problem. Now, let us see the another form, that is the non-homogeneous linear ordinary differential equation. So, in this case the Rx is not equal to 0. So, we have this particular form. Okay. Now, when you have this particular form, we can again solve it, and for solving I am not going into the detail of the solution derivation. I am just giving you the final expression to solve it. So, what we are doing, the solution will be yx equal to e to the power minus h into this integration e to the power h r dx plus c, and h is nothing but this integration of px dx. Okay. So, when you have this particular thing, then you can solve this for this integration. If it is a simple expression, you can integrate it analytically, and if the expression is complex, then you should use any numerical technique for finding this, doing this integration. So, I shall be talking something about this numerical integration and numerical differentiation in my future lectures. So, this is the way you can solve this for y. Now, let us take an example of the non-homogeneous linear ODE. So, here we have a question which is from some biotechnological applications. Here we have that hormone level in the blood of a patient is maintained by continuous injection and withdrawal of the hormone to and from the body. Okay. So, it is a patient, so to make a balance of the hormone, maybe some gland is not working properly, and you know that in our biological systems there are many glands are involved in secreting the hormones to maintain our body activities. So, if some gland is not working, we will find there will be hormonal imbalances. For example, insulin may not be secreted properly, so that our sugar level in the blood will keep on fluctuating. So, for treatment of all these things, what is being done, that you are injecting and also withdrawing the hormone from the body. The injection is done in a periodic fashion that may be taken as a sinusoidal change, while the rate of removal is maintained constant. Okay. So, this kind of a situation we are considering, that the removal rate is constant, but the injection rate is periodically varied, and for simplicity's sake we are assuming this periodicity may be represented as a sinusoidal wave. And perhaps you know, when we talk of sinusoidal wave, what we mean is this: we have some kind of an amplitude and a time period. Okay. So, this kind of a sinusoidal wave. So, this is the kind of thing we are talking about. Okay. So, these are kind of way we are assuming that it is periodically getting injected to the system. So, this process may be represented by the following differential equation to determine the hormone level in the blood at any time. So, this is the particular expression. Again, we are not going to the equation how it has been derived, but this is the final expression to know the hormonal level in the blood. And here this A, B, K, A, B and K are taken to be constant, and this omega may be changed by the user. Now, let us see that how to solve this kind of a problem. Here we have, this is the expression given, and when we put this in terms of the generalized expression, we find this is y prime plus pt into y plus rt. And now, if we see that here pt is nothing but k, and this RT is nothing but the whole of the right hand side. Okay. Now, when we have this yt equal to e to the power minus h, and this integration e to the power h r dt plus c, and h is this. Now, as I said that by comparison we can see p is a constant and h is kt and r is a plus b into p cos omega t. Now, once we know this, what we do? Now, we simply take this h to be this particular thing from our expression, and we put all these things over dt, e to the power h into r we do here. Okay. And now, because this is quite a simple expression for integration, so we can carry out the integration, and we find that we will be having this kind of an expression. Okay. And when we rearrange it, we will get this particular expression. Now, what you find in this expression is this, that this particular term is the sinusoidal term, and this particular term is going to get diminished with time. Okay. So, this particular term is kind of giving us the transient change in the hormone level in the blood. Okay. And if this term goes, whatever we are left with will be giving us some steady variation of the hormonal level in the blood. So, what we say here is this a transient term, because as the total solution is this. Okay. So, this by this particular violet line we are saying that we have the total solution, and when as we see that for this one we see that as time goes to infinity, we find that e to the power minus k t tends to 0. Okay. That means what? That at long time this term will vanish. So, this thing we shall be left with. Okay. And this is giving rise to a sinusoidal form. So, this particular this red colored one is giving us the steady state solution. Okay. So, now if we plot this particular expression, we can see that how we shall be able to this what kind of variation is this the variation of thing, and now what we are doing is we are trying to find out the value of the integration constant. So, from our problem we take that initial value of y as that at time t equal to 0, we say that there is no hormonal thing. This 0 means what? That it is not that we have 0 hormone, it is something some base value, because we are here we are not really interested to know the exact value of the hormone in the blood. Here we are trying to see that from some base value how the hormonal level is fluctuating. Okay. So, you can say like this, that we have some base value over here. Suppose we take this base value, this is we call it nominal value, this one, and over this how the things are fluctuating. So, we can put it like this, and many times we do this kind of analysis instead of getting the exact value of the particular variable, we take what we call the difference variable, and this concept you can also see in the enthalpies etc. And in control systems we also talk about the difference variable rather than the exact variable, to check that how much we are fluctuating or deviating from the nominal value or some kind of set point, okay, for the given parameter. So, here we are using the same kind of concept here, that is why we are putting that y equal to 0, and it should not be interpreted as if there is no hormone at t equal to 0, but should be taken as the hormone level is exactly what is desired in the blood. Okay. So, with this particular initial condition, we can see this is the value of C, and here we are putting the value of the constant of integration. And now, with this manipulation, if we take the value of the A and B to be 1 and K to be 0.05, we have this typical fluctuation of the y with respect to time, and you can see that initially we can see that this region is giving us the transient, and this is coming from this C e to the power minus t term. Okay. So, this thing is coming from this, and ultimately we find that this term dies down, and in this region we are getting the steady state solution, where we are finding this has assumed a periodic fluctuation of the hormone level in the blood. Okay. So, similar kind of problems are also there in many other fields you may find, and you have to treat these problems in this particular fashion. Now, we shall look into non-linear ODE, and in this case what we do, that we get the solution by linearizing the non-linear ODE. Okay. And one of the methods is to do by Bernoulli equation. Please do not confuse this particular with the energy balance we have derived earlier, and we named it Bernoulli equation. Okay. This particular method was proposed by Bernoulli, the same scientist. Okay. Now, here we have this particular expression for the nonlinear ODE, and in my earlier lecture I told you what we mean by linear and nonlinear equation. Okay. Now, A is a real number which is here, and if A equal to 0 or 1, we have the linear ODE, okay, linear equation. So, without again going into the detail of the solution, here we have the final Bernoulli equation. He suggests that you make this particular transformation. So, you put another variable u and put that as y to the power 1 minus a. And with this particular thing, you just replace in this equation and you get per this equation. Now, you can see that on the right hand side, we have totally taken off the any dependency on the u, okay, and we have linearized the original nonlinear equation in terms of some transformed variable. Okay. So, that means what we shall be solving for will be u, and once we know the value of u, we can now solve for y. Okay. So, let us take an example problem. So, here we have one equation which is called a logistic equation or the Verhulst equation, which is used to find the populations of different types of species in the world like plants, animals or humans, and how this population varies with time. So, this is the equation. Okay. Now, you can see this particular equation is a non-linear equation. So, we rearrange the equation like this, and if you put in the form we just presented in earlier, we find that y prime plus p x y is equal to g x y to the power a, and now we compare this thing, we find that p x is nothing but minus a, and a is 2 here and g x is minus b. So, incidentally p x and g x are constants. And now, what we do the transformation as we suggested, that u is equal to y to the power 1 minus a, that is 1 minus 2, and is equal to 1 y to the power minus 1, that is equal to 1 by y. And this is the when we differentiate with respect to this u with respect to y, we get u prime equal to minus 1 by y square into y prime. Okay. Now, that means u prime equal to this particular expression, and here we have this, simply we are doing the mathematical manipulations with respect to the original equation. So, here this you can easily see that u prime will be equal to b minus a to the a by y, okay, and this we know that this is equal to u. So, we simply replace this 1 by y with u, and we get ultimately this particular expression which is a linear equation, and we know that have learnt how to solve this linear equation, and this is the particular solution of the linear equation. And again we are having this particular constant c, whose value may be obtained by the initial condition prescribed in the particular problem. Okay. Now, we know that we have obtained u, now we can find the value of y by simply taking the reciprocal of u, and this is the final solution for y. Okay. And here again we shall see that this particular is showing a transient state, and as t goes to infinity, we find this particular term tends towards 0. That means that at steady state this y value will be a by b. That means all the populations, whatever may be the initial state, they always be converging to this steady state value, and this has been shown in this particular graph. You can see that we choose different value of a by b. So, whatever value of a by b we choose over the period of time, we find that they show different type of the variations. That means some of them are decaying and some of them are showing growth. Okay. But ultimately, whether it is decaying or growing, ultimately we find all of them tend to converge to the value of the particular a by b. Okay. So, this is the y and this is the time. Okay. So, this is one for some given a by b ratio, you can change the value of a by b ratio, you will find that you are converging to different values of the population, and of course, this a by b will be determined by the local factor, the geographical factor, or the demographic factors will be coming into action whenever you are deciding the population of any species in the world. Now, you can look into these references for more detail and more examples on these particular topics. Thank you.